All right, so yeah, my name's Cameron Murray. I'm an assistant professor at the University of Arkansas, and I'm going to share some research we've done. Mostly, I'll talk about some work we've done on reinforced concrete made with BCSA cement. I also have some slides on some mixed design work we've done and some kind of ongoing stuff we have. So a little bit of everything here. I want to acknowledge the students that did the work that I'm sharing. Gabe Cook did all the flexural testing I'm going to show. Edgar Soriano and Gerardo Aguilar did the mixed design guidance. And I'm showing a little bit from Caleb Chestnut. He's still working on his master's thesis, but he's been working on some shear strength stuff with BCSA. So first, I thought I'd give some background on what BCSA is. And in order to talk about BCSA, Belitic calcium sulfoaluminate, we need to talk about what CSA is. I think there's some misunderstanding or miscommunication. People talk about CSA cement as if it's one cement, but technically it's just a compound in cement. So just like A-lite or B-lite in Portland cement, it's one part of a cement, and different cements that contain CSA can behave differently. It's also known as Eulemite or Klein's compound. It's called that because it was invented by Alexander Klein in the 50s and 60s at UCLA. And I put the patent number up here. You know, at that time, researchers were very interested in counteracting shrinkage in Portland cement and developing expansive cements. So that's what Klein was aiming at initially when he invented it. CSA is still used in this capacity as type K shrinkage compensating cement. A lot of CSA cements tend to be faster setting, have faster strength gain. They can tend to be expansive, but again, it all depends on the composition of the particular cement, how much CSA it has in it. Initially, these cements were quite popular, it seems, in the 60s and 70s. The popularity kind of waned over time in the United States, but there's some more interest because of its environmental friendliness now. But in China, it's been used on a very wide scale for a long time. CSA cements are known as the third cement series there. So when CSA cements react with water, the reaction products are a little bit different. So this is a SEM photo we took at the University of Arkansas. So you can see all these needle-like structures. These are ettringite. This is what primarily forms when CSA reacts with water. This is what makes it expansive and gives it faster strength gain. So BCSA cement, I've got a comparison here of Portland cement and BCSA in terms of their composition, what cement compounds are in them. And so for BCSA, you can see over here it has about 30% CSA. And actually, it has more B-lite than CSA, so about 45% B-lite compared to about 17 in Portland cement. And so that B-lite kind of slows down the expansion. It should provide better later age strengths. So that's BCSA and where it stands as a subset of CSA cements in general. BCSA, a benefit of it compared to some of the other alternative cements is that it can be mixed very similarly to Portland cement. So you just add water and mix it up. It tends to have a very fast setting time, less than 20 minutes. So basically you have to use a retarder in order to use it for most applications. It also has very fast strength gain. We can usually achieve 4,000 PSI in less than two hours pretty easily. As far as setting time goes, the set retarder that we've used mostly at the University of Arkansas is citric acid, which is a food grade citric acid. And we did some setting time tests with the mortar penetrometer. And we found that if you don't use any citric acid, the cement sets up in just over 10 minutes, but that the setting time can be increased linearly with increasing citric acid dosage. And if you look in the middle of this figure, around a 0.35% dosage of citric acid by cement weight is usually what we use. And that's good for about 45 minutes of working time. But we haven't found too many negative effects with adding additional citric acid after that. Some other benefits of BCSA, it's a low shrinkage material compared to Portland cement. It's got good ASR resistance, good sulfate resistance. Of course, you know, weighed against Portland cement, every alternative cement is going to have advantages and disadvantages. BCSA is more expensive than Portland cement, and there's some ongoing research questions about carbonation and corrosion, and I think maybe Lisa has some of that in her presentation. So again, you have to use a retarder, but one thing we've been working on recently is developing some kind of general mix design guidance here. So one of the things we wanted to look at was the relationship between the water content of mixtures with BCSA cement and the slump. And so these are concrete mixtures we made. I should say that we basically always use a high range water reducer. The graph I'm about to show doesn't include any super plasticizer, but it's just useful to have a more fluid mixture so that you can consolidate it more easily since you're fighting the clock in terms of the setting time. So what I have here is slump on the y-axis and water content on the x-axis, and this gray line is what ACI 211 says is the rough relationship between slump and water content for the size of aggregate that we use at the University of Arkansas. So we made some BCSA mixtures at different water contents and different citric acid dosages and compared to this guidance. And so you can see if you don't use any citric acid at low water contents down here, it's very difficult to achieve any slump at all. Again, I don't recommend ever not using citric acid, but additional citric acid improves the workability for the same water content. So this is the 0.35% citric acid dosage we usually use. That's good for about 45 minutes of working time. And then if we increase citric acid dosage from there, we still get some additional slump benefit. So it's quite different from Portland cement in terms of slump. You can see that these curves are concave down instead of that concave up relationship in ACI 211. We've also looked at some water cement ratio and strength relationships for BCSA. So what I have on the slide here now are 3-hour strengths at 3 different water cement ratios and 4 different citric acid doses. So you can see at a 0.4 water cement ratio at 3 hours, we're achieving more than 4,000 PSI, even up to a 0.7% citric acid dosage. When we go up to 2, which is probably far higher than you would ever use in one of these mixtures, that's taking you way out to like Portland cement setting times. There's obviously no strength at 3 hours. But just like Portland, there's a relationship between water cement ratio and strength of the mixtures that's quite similar. When I started working with this cement, I'd heard that it needs a lot more water to hydrate properly. But I mean, I've kind of found that similar water cement ratios work well for Portland cement and BCSA cement. And at 28 days, these are the strengths. So the strength continues to develop well on after 3 hours. And so you can see at a 0.4 water cement ratio, we're getting strengths up around 7,000 PSI. And the strengths are still quite good at higher water cement ratios. One other point I should make is these mixtures that have 0% citric acid, our strengths were quite good, but these were very hard to consolidate. As you saw from the slump figure, it's hard to get a good slump out of mixtures with no citric acid. So again, I probably would not recommend doing these mixtures without any set retarder. So I thought I'd give a little bit of background on why I became interested in working on this. When I was at OU, I was fortunate to help out on some work with pre-stressed concrete made with BCSA cement. The impetus for this work is that a material like this that has low shrinkage and sets up really quickly is an ideal material for precast and pre-stressed concrete. So we made a series of beams at OU and tested them. Specifically, we were looking at bond and pre-stress transfer. And we found that it behaved very similarly to Portland cement in terms of those components of its performance. And then when I came to Arkansas, the new ACI code came out, and there's a clause in the ACI code that allows design professionals to use alternative cements if they choose to, as long as they can prove that these cements provide the same performance requirements, so structural, fire, and durability. And there's a really good rundown of what's implied in this in a Concrete International article from a couple years ago that I recommend reading. But this made me want to look at BCSA cement and its flexural and shear performance and other parts of its structural performance other than what we did on pre-stressed concrete. So my first student at the University of Arkansas, Gabe Cook, and we made a series of reinforced concrete beams. This is what they looked like. They were a little over 12 feet long. They had a 12-foot span length. We applied a point load in the middle with a spreader beam. So we ended up with a constant moment section in the middle part of this beam to investigate just the flexural performance of BCSA cement. And we did a comparison between Portland cement and BCSA cement. So we made 12 total beams. We made 6 that were tension controlled sections and 6 that were compression controlled. And I'll just share the tension controlled ones here today because they're a little bit more interesting than the compression controlled. And I guess you can take my word on it that the compression controlled performed well the same way as the tension controlled, or you can go read the paper if you don't believe me. This is what our tension controlled cross sections looked like. So the beams were 6 inches wide and 12 inches deep, and they had 2 number 6 rebars in the bottom, and they had enough shear reinforcement that we knew we were going to get a flexural type failure. Of those 6 tension controlled beams, we had 2 Portland cement control beams that we tested at 35 days of age. These were made out of the same mixture. They were from ready mixed concrete. We had 2 BCSA cement beams that we tested at 2 to 5 hours. So the reason there's a range there is this is kind of as soon as we could get the beams out of the forms and put them in the loading frame and test them, that was when the test was performed. And we also had 2 BCSA cement beams that we tested at 1 day of age. And the reason that we did 1 day is because at this age, their strengths were very similar to the Portland cement beams. So we were kind of testing the very early strength of the beams, as well as the strength of the beams whenever the compressive strength was similar to our Portland cement controls. This is what our mixture designs look like. So BCSA is on the left here and Portland cement is on the right. We tried to match the quantity of cement and coarse aggregate because we figured these were going to have some impact on the flexural performance. But you see we have a different water cement ratio, slightly different fine aggregate content, and this is just because the specific gravity of these cements is a little bit different. But there's also more high range in the BCSA beams. And as I mentioned before, we just tend to use high range so that we can get it into the forms quickly, where it can self-consolidate a little bit, so we're not spending a bunch of time getting it consolidated into the forms. And we used a 0.35% citric acid dosage here. This is expressed in terms of this solution of citric acid that we make, that we use in 9 fluid ounces. So in terms of slump, the BCSA beams were between 7¼ and 10¼ inch slump. Our average strengths for the BCSA cement beams were 4,000 PSI at 2 to 5 hours and a little over 6,700 PSI at 1 day. And you can see that just about matches the strength of the Portland cement mixtures on the day that we tested them. So this was nice. We had a kind of a direct comparison between 2 mixtures that had similar strengths. This is what our beams looked like in the loading frame after they were tested. So they're simply supported. You can kind of see the cracking pattern. You can see where the concrete crushed here in the middle. And you can see LVDTs that we use there to measure the deflection at the loading points. So the first thing that we compared with these is just kind of general qualitative behavior. How much cracking is there? Did we achieve a flexural failure? So this is one of the tension controlled Portland cement beams, and you'll notice there's a lot of distributed cracking. There's a compression failure. That's that shaded area at the top between the load points. So this looks like a flexural failure. That's good. For the BCSA beams that we tested at 2 to 5 hours, this is what one of those looked like. And again, lots of distributed cracking. There's compression failure in the middle. The extent of cracking looks quite similar to the Portland cement beams. And the same goes for the BCSA beams that we tested at 1 day of age. The performance of these, just from a qualitative standpoint, look very similar. So the next thing we had to look at is the load versus deflection relationship. So load is on the y-axis here, deflection on the x. What's shown here are the 2 Portland cement tension controlled beams. And so just some general things about this if you're not used to looking at these. we start at 0, 0. There's a slope change when the beam cracks. Then there's a linear slope deflection relationship up until yielding here. And then the beam loses a lot of stiffness as the steel yields. And then the concrete crushes somewhere out here. And that's the moment capacity. So if we plot the BCSA beams on here that were tested at 2 to 5 hours as soon as we could get them out of the forms and into the load frame, you can see they plot right on top of the Portland cement beams. And the Portland cement beams came out of the exact same batch of concrete. These BCSA beams were actually 2 separate batches, but you can see we got really consistent performance. The cracking looks like it occurs at about the same time. Yielding occurred at about the same time. We actually appear to have a little bit more ductility before the BCSA beams crushed. And then if I plot the BCSA beams that were tested at 1 day of age on here, you can see they're a little bit stiffer, but basically they perform the same way. Similar cracking loads, similar yield point, similar load versus deflection failure after the yield. So that's all good. Another way to compare these is to take the experimental moment capacity, the maximum moment that the beam achieved, and divide by the nominal moment capacity in the ACI equation or in the ACI code. And so a number greater than 1 here is a good thing. That means that our capacity exceeded the estimate or the predicted capacity. And you can see for all of our beams, we were around 1.2, including all the BCSA beams. They were quite consistent with the Portland cement. So another thing we looked at is something that's known as the ductility index. It's a way of comparing beams in terms of how ductile they are. So what we do is we look at the yielding and the ultimate point on the beam's load versus deflection curve. The distance between these is kind of an indicator of ductility. We want more space between these 2 values. So we take the deflection at ultimate and the deflection at yield, and the ratio of those 2 numbers is the ductility index. So a bigger number here is good. It means more ductility, more warning before a failure or before the concrete crushes. And so what we found is the BCSA beams were more ductile than the Portland cement. So the ductility index for the Portland cement beams was about 1.5. It was 2 for the beams that we tested at 2 to 5 hours made with BCSA cement, and it was around 2.5 for the BCSA beams tested at 1 day. And so that's good, but what's really interesting about this is that the compressive strength of those beams tested at 2 to 5 hours was actually less than the Portland cement beams. So this increase in ductility was unrelated to the strength. And so basically the point where this concrete crushes out here is defined by the ultimate compression strain that the concrete can carry. And so we believe that this phenomenon is somehow related to an increased strain capacity in the cement. Which would be beneficial for design. That would allow you to use more steel in the section, use more efficient sections without sacrificing any safety or ductility. So we found that cracking behavior was very similar between the Portland cement and BCSA cement beams. The load deflection behavior was similar. The moment capacities were similar, but we actually had this improved ductility that potentially points to a higher ultimate compression strain. So what we've been working on now, we were fortunate enough to receive a Concrete Research Council project to look into this ultimate compression strain issue, look into the stress strain distribution for this cement. So we're recreating some of these eccentric bracket test specimens. This is kind of the same type of work that was done to develop the ACI flexural strength equations. So it's kind of a crazy looking setup, but we basically have this concrete sample here in the middle. We apply an axial force and a moment to it so that we have 0 strain on one face and an ultimate strain on the other, and see what the strain distribution is. I mentioned my student Caleb. He's working on shear strength, so a very similar study, just looking at shear. And he's found that so far shear strength of these BCSA cement beams is really similar to Portland cement in terms of strength and behavior. And you can see there's a BCSA one on top of a Portland cement one there. The cracking's quite similar. So he's working on finishing that up this fall. And I know I'm going a bit long, but if you'll indulge me, I have one more thing I wanted to share with you all. My colleague and I recently did an experiment where we made a little testing rig and pulled out our nose hairs and determined how much force it took to pull them out. Our goal with this was to win something called an Ig Nobel Prize. And we actually had the work published in a first quartile materials engineering journal called Materialia. And so I hope you'll go and read this paper. And if you find it funny, you could go to the Ig Nobel website and nominate us for a prize. So that's all I have. Thanks for your time.
Thanks, Cameron. That's really nice work and a hilarious paper. I'll definitely check it out. We have a whole bunch of questions. I answered one already. I think that you and I tend to dose retarders similarly, but the question was, when you state 0.35% citric acid dosage, is that like saying 0.35 ounces per cement weight, to put it into terms of admixture dosage? And I said we do it as a percent of the cement weight. So like 100 grams of cement would have a 0.35 gram citric acid dosage.
Yeah, that's correct. But that's a good point. We actually make like an admixture. So we mix up 5 pounds of citric acid per gallon of water and dose it that way. But yeah, that's correct about the dosage.
Okay, another person asked if you're aware of any work that's been done to correlate water to cementitious materials with the exposure categories for durability. So like, can you say that using a 0.4 water to cement ratio, CSA is equivalent to using a 0.4 water to cement ratio for an F3 exposure category?
Yeah, I don't know. I think that would be really good to do. I'm not familiar with any work like that.
Okay, I didn't want to preempt you, but I think the answer to that is that relatively little exposure and durability work has been done. So definitely nothing to correlate it with code, although there is some kind of extraneous work just floating out there. Okay, so another person asked what method of curing you used with your beams?
Yeah, so all the beams are just kept in kind of a lab environment. So they're not controlled for humidity, but they're kind of at room temperature. Although the shear specimens that we made, we stored several of them outside for a year. So
can you tell us again what the compressive strength of the BCSA concrete was at 28 days? Or I guess you didn't tell us at 28 days. Did you track that?
We have not looked at modulus of rupture.
Oh, compressive.
I would be surprised if there's a decrease. Oh, sorry, the compressive strength. It depends on the water cement ratio, but at a 0.4, you can get up to 8,000 or 9,000 PSI, depending on what citric acid dosage you use.
And then I guess you had noticed the follow-up question. Was there a decrease in MOR?
Yeah, so I haven't directly measured MOR, so I can't say. That would kind of surprise me. I know that they've pulled beams out of airport runways and done MOR and seen increases in the MOR over longer periods than 28 days, but I can't say for sure.
I know we had measured MOR when I was at Georgia Tech. Sean Alapati is on this in the panel, may have some data on that if he wants to respond later. And then the last question is, does using a lower than a recommended water to cement ratio cause any concern for latent expansion?
Yeah, I hate to just say I don't know to every single question. I haven't measured that specifically. People have looked at expansion a lot, and I know that moisture certainly affects the amount of expansion you get from any CSA cement. So it probably depends a little bit on the water cement ratio and on the humidity that it's stored in.
My guess is that question may have to do with your comment about using higher water cement ratios with CSAs, but just like you were suggesting, that higher water cement ratio of 0.72 that's suggested is relative to the yeelimite component only, and doesn't include all of the extra belite and anhydrite and everything that's in the mix. So what you said about it being equivalent to Portland cement water cement ratio wise, I found that.
I guess it's kind of like saying, well, you only need a 0.28 water cement ratio for Portland cement, but you probably wouldn't really want to use that for most concrete.